Hello everyone, I hope you are well and are curious because today's topic is something we don't usually talk about on a day-to-day basis. Today we are learning about gravity and how it affects everything around us. Let's start by defining gravity. First, what is gravity to you? What does it do? And how does it affect you? Next, find a spot in your space and count to 3. We're going to jump at the same time. I'm going to jump in my chair just so I don't have to move around my frame too much. Ready? 1, 2, 3, jump. Ow. Thank you, gravity, for pulling me back down. Gravity is a natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, and even light, are brought toward one another. On Earth, gravity gives weight to physical objects, and the moon's gravity causes the ocean tides. Let's also define mass and energy, as they play a key role in gravity. Mass is both a property of a physical body and a measure of its resistance to acceleration when a net force is applied to it. An object's mass also determines the strength of its gravitational attraction to other bodies. Energy is the quantitative property that must be transferred to an object in order to perform work on or to heat the object. Energy is a conserved quantity, and the law of conservation of energy states that energy can be converted in form, but not created or destroyed. So what does that mean? Well, let's break it down. The gravity here on Earth is what keeps you on the ground. The gravity of the sun is what keeps Earth in orbit around the sun, and the gravity of the Milky Way keeps the solar system orbiting around it. Gravity is everywhere. No matter where you look, it's there. Have you ever been to a store where you have a coin donation funnel, and you drop a coin in, and it orbits around the center before falling into the collection bin? Well, it's a good representation of how gravity works and how space-time is bent to gravity. As the quarter orbits, it loses velocity and therefore loses energy, and it can't maintain a steady orbit like Earth can against the sun. So as it loses energy, it falls closer and closer to the center. Stars are some of the largest celestial bodies that we know of. Check out the scale of our sun compared to other stars we've discovered. Some stars at the end of their life cycle explode into a supernova, or others collapse into a white dwarf like our sun will one day, while others collapse in themselves with so much mass and so much force they create a singularity we call a black hole. It's called a black hole because its gravitational force is so powerful, not even light can escape it. That point of no return is called the event horizon. The only thing that has been detected to be emitted by black holes is Hawking radiation, named after Stephen Hawking, who proved its theoretical existence in 1974. Hawking radiation is a thermal radiation, meaning heat, being emitted just outside the event horizon, and this is emitted due to the reduction of mass inside the black hole, leading to the black hole's eventual evaporation. We can't see what's inside of a black hole, so we don't know how it works inside, but we can make a really good prediction of what's going on inside. Why is learning about gravity important? If we want to put satellites into orbit, we have to launch them with just enough energy to sustain a stable orbit, and if we eventually want to colonize the moon and Mars, we have to launch rockets that can escape Earth's gravity beyond low orbit. It's also important on discovering potentially habitable planets and other systems that lie inside of the Goldilocks Zone. This is the zone where a celestial body needs to be warm enough to have liquid water and far enough away that it doesn't get too cold to freeze over. So it can't be too hot and too close, can't be too cold and too far, it has to be just right in the middle. In our solar system, Earth and Mars are the only 2 planets inside of our Goldilocks Zone. Now, the more gravity there is somewhere, the slower time moves relative to them outside of that area. So, as an example, if I were orbiting around the sun, if I was orbiting around a black hole really close to the event horizon, because the gravity there is so intense and I'm able to stay outside of it, time for me would slow down to a crawl compared to you. If you were to look at me going to that black hole, eventually it would get to a point to where you would just see me very slowly inching closer and closer to the black hole. But to me, I'm actually still orbiting around it because time is moving faster for me relative to you. But to you, I'm moving very slow. Does that make sense? Here's a video that explains how relativity works. An example of relativity is in the movie Interstellar. When they go down to Miller's planet, which is covered in water, and there's these giant tidal waves that are caused by the tides of Gargantua, the time dilation there is for every 1 hour they're on that planet, it's 7 years back on Earth. Again, because their time is slowed down relative to Earth. And we have to say relative because time isn't equal everywhere. It moves slower in some places than others because there's more gravity. Alright everyone, I hope you enjoyed today's video. I will see you in the next one. If you're going to be in my Zoom call later today, the day of upload, I will see you there. If not, thanks for watching. See you later. Bye!